Let's start with something you already know, something so familiar you probably never think about it. Right now, wherever you are, you're touching something. Maybe it's a pillow under your head, maybe it's the mattress beneath your back, or a blanket draped across your legs. You can feel it. It's solid. It's real. It has weight and texture and warmth. Your body presses against it, and it presses right back. That's just how the world works, right? Solid things are solid. You can't push your hand through a table. You can't walk through walls. Your feet don't sink through the floor. Everything feels reliable, dependable, firm. But here's the thing. Every single one of those solid objects, every table, every wall, every floor, every bone in your body, is made of atoms. And atoms, as it turns out, are almost entirely empty space. Not mostly empty, not kind of empty. We're talking about 99.99999999999% empty. That's not an exaggeration. That's the actual number. If you could somehow strip away all the empty space inside every atom in your body, if you could compress just the solid bits down into a tiny ball, all the actual matter in you would fit into a space smaller than a grain of sand. Actually, smaller than that. It would be a speck so tiny you wouldn't be able to see it without a powerful microscope. Think about that for a second. You, right now, this warm, breathing, thinking person, lying here in the dark, are almost entirely made of nothing. The matter that makes up your body is overwhelmingly empty, and the same is true for everything around you. The walls of your room, the ground beneath your building, the entire earth itself. If you squeezed out all the empty space in every atom on the planet, the whole thing would compress down to something about the size of a marble. The entire earth. A marble. So here's the question that should be keeping you up tonight, except we're going to let it gently carry you to sleep instead. If atoms are that empty, if you and the pillow and the mattress are all almost entirely nothing, then why can't you pass through any of it? Why does the world feel solid? Why does anything feel like anything at all? It's a genuinely wonderful question, and the answer takes us deep into the heart of what matter actually is, how atoms really work, and why the universe is far stranger and more elegant than it looks from the surface. So settle in, get comfortable. We've got a long, beautiful trip to take through the invisible architecture of everything around you. Let's start at the beginning, or at least at one particularly dramatic beginning. The year is 1909. The place is Manchester, England, inside a cramped, dim laboratory at the university. A physicist named Ernest Rutherford is running an experiment. Rutherford is a New Zealander, big and boisterous, with a loud voice and a walrus mustache, and the kind of relentless curiosity that makes him impossible to work for and impossible not to admire. He's already won a Nobel Prize, actually, for his work on radioactivity, but he considers himself a physicist first and foremost, and he's got a hunch that the atom isn't what everyone thinks it is. At this point in history, the prevailing model of the atom is something called the plum pudding model, proposed by J.J. Thomson, who had discovered the electron about a decade earlier. In Thomson's picture, the atom is a blob of positive charge, like a pudding, with tiny negative electrons embedded in it, like raisins scattered through the dough. It's a nice, tidy picture. The positive and negative charges balance out. The atom is neutral, and everything makes sense. Most physicists are perfectly happy with it. Rutherford isn't so sure. He wants to probe the inside of the atom, to see what's actually in there. And his tool for doing this is a beam of alpha particles, which are basically helium nuclei, little positively charged projectiles that get shot out by radioactive materials. His plan is beautifully simple. Take a thin sheet of gold foil, so thin it's only a few thousand atoms thick, and fire alpha particles at it. If Thomson's plum pudding model is right, the alpha particles should sail straight through. The positive charge in each atom is supposed to be spread out evenly, like a diffuse cloud, so there's nothing dense enough to deflect the fast-moving alpha particles. They should pass through the foil like bullets through fog. Rutherford assigns the actual experiment to two younger scientists, Hans Geiger, yes, the Geiger counter guy, and Ernest Marsden, who's still an undergraduate at the time. They set up their apparatus in a darkened room because they're detecting the alpha particles by watching for tiny flashes of light on a zinc sulfide screen. Every time an alpha particle hits the screen, it makes a faint sparkle, and Geiger and Marsden have to sit in the dark, watching and counting flashes for hours on end. It's tedious, painstaking, eye-straining work, and at first, everything goes exactly as expected. Most of the alpha particles sail straight through the gold foil, barely deflecting at all, just as the plum pudding model predicts. But then, something strange starts happening. A few of the alpha particles are bouncing back, not just deflecting slightly, not just nudging off course, but bouncing almost straight back toward the source. Some of them are coming back at angles greater than 90 degrees. It's as if you fired a bullet at a sheet of tissue paper, and the bullet ricocheted back and hit you in the face. Rutherford, when he hears about this, is floored. He later describes it as the most incredible event of his life. And this is a man who had already won a Nobel Prize. He says it was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. That analogy tells you everything about how shocking this result was. And here's what makes it even more striking. It wasn't most of the alpha particles bouncing back. It was about 1 in every 8,000. The vast majority still sailed through the foil as if it wasn't there. But that tiny fraction, that 1 in 8,000, was doing something that was physically impossible under the plum pudding model. If the positive charge in an atom were really spread out like a diffuse cloud, nothing could deflect an alpha particle that violently. The only explanation, the only way to make the math work, is if all the positive charge and nearly all the mass of the atom is concentrated in an incredibly tiny, incredibly dense point at the center. That point is what Rutherford called the nucleus. And when he worked out how small it had to be to produce the deflections Geiger and Marsden were seeing, the number was staggering. The nucleus of an atom is roughly 100,000 times smaller than the atom itself. Let me say that again, because it's easy for that number to just wash over you. The nucleus is 100,000th the size of the atom. If the atom were the size of a football stadium, the nucleus would be a single fly, sitting on the 50-yard line. Everything else, all that space between the outer edge of the atom and the nucleus at the center, is empty. There is nothing there. Just the electrons, those tiny particles that Thomson discovered, orbiting somewhere in that vast emptiness. This is the moment when physics realized that matter is almost entirely empty space, not as a metaphor, not as a poetic observation, as a measured, experimentally verified fact. The stuff you're made of, the stuff everything is made of, is overwhelmingly nothing. And the question that immediately follows is the one we started with. If the atom is that empty, if there's all that space between the nucleus and the electrons, then why can't things just pass through each other? When you put your hand on a table, the atoms in your hand and the atoms in the table are both almost entirely empty space. Why don't they just slide through each other, like two clouds of fog overlapping? This is where the story gets really interesting, because the answer isn't what you might expect. It's not that there's some hidden solid stuff inside the atom that we missed. There isn't. The emptiness is real. The answer is that solidity, the feeling of things being solid, has almost nothing to do with physical stuff being in the way. It's about forces. Invisible, powerful, deeply strange forces that operate at scales so small you can't even begin to see them. Let's build this up step by step, because it's one of the most beautiful explanations in all of physics, and it deserves to be understood properly. The first piece of the puzzle is electromagnetism. You know about electric charge, at least in a general way. There are two kinds, positive and negative. Like charges repel each other, opposite charges attract. That's the basic rule, and it governs an astonishing amount of what happens in the physical world. Now, think about what an atom looks like. You've got a nucleus at the center, which is positively charged, because it's made of protons, which carry positive charge, and neutrons, which are neutral. Orbiting around that nucleus, somewhere in the vast empty space of the atom, you've got electrons, which are negatively charged. The electrons are attracted to the nucleus because of the electromagnetic force. Opposite charges pulling on each other, and that's what keeps the atom together. So far, so good. But here's where it matters for our question about solidity. When two atoms get close to each other, the thing that meets first isn't the nuclei. The nuclei are buried deep inside, in that tiny central point. The thing that meets first is the electron clouds, the outer edges of each atom, the regions where the electrons are doing their thing, and electrons are negatively charged, both of them. So when two atoms approach each other, you've got negative charges coming close to other negative charges, and like charges repel. This electromagnetic repulsion is the first reason you can't push your hand through a table. When the atoms in your skin get close to the atoms in the table's surface, the electron clouds start pushing against each other. They repel, and this repulsive force gets stronger the closer the atoms get, much stronger. It ramps up incredibly fast. So even though both your hand and the table are mostly empty space, the electromagnetic force between their electron clouds creates what effectively feels like a wall, an invisible wall of repulsion that prevents the atoms from getting any closer. And this, by the way, is what touching actually means. At the atomic level, when you touch something, your atoms never actually make contact with the atoms of the thing you're touching, not even close. There's always a gap, always a tiny space between them, held open by this electromagnetic repulsion. What you feel as touch, as pressure, as solidity, is the force of trillions upon trillions of electron clouds pushing against each other. You have never truly touched anything in your entire life. Not in the sense of atom meeting atom, matter pressing against matter. Every touch you've ever felt has been a force field interaction. Think about that. Every hug you've ever given, every hand you've ever held, every time you've pressed your fingers against someone's cheek or felt the warmth of another person next to you, there was always a tiny gap, always a buffer of electromagnetic force between you. You've been interacting through force fields your whole life, like some kind of science fiction scenario, except it's not fiction. It's just how atoms work. But here's the thing. Electromagnetic repulsion is real, and it's important, but it's not actually the whole story of why matter feels solid. If it were just about electric charges pushing each other away, you could, in principle, overcome that repulsion with enough force. Push hard enough, and you'd squeeze the electron clouds together, force the atoms to overlap. And while it's true that this electromagnetic repulsion is enormous at atomic scales, there's a deeper reason, a more fundamental reason, why matter holds its shape. And this one comes from quantum mechanics. To get there, we need to talk about what electrons actually are and how they actually behave. Because the picture most people carry around in their heads, the one with little electrons orbiting the nucleus like planets orbiting the sun, is deeply, fundamentally wrong. Not just slightly off, wrong in a way that matters enormously for understanding why the world feels the way it does. The solar system model of the atom is the one you probably learned in school, and it has a nice, satisfying simplicity to it. The nucleus is the sun. The electrons are the planets. They orbit in neat circles at fixed distances. It's clean. It's intuitive. And it was the first model that Rutherford and his colleagues came up with after the gold foil experiment. But it has a fatal flaw. Here's the problem. An electron is a charged particle, and according to classical electromagnetism, Maxwell's equations, the beautiful framework that describes how electric and magnetic fields work, a charged particle that's accelerating must radiate energy. It has to. It's built into the mathematics. And an electron orbiting a nucleus is accelerating because it's constantly changing direction, even if it's going at a constant speed. Circular motion is acceleration, so a classical orbiting electron would constantly be emitting electromagnetic radiation, losing energy with every orbit. And as it lost energy, it would spiral inward, closer and closer to the nucleus, radiating faster and faster, until in about 100 millionth of a second, it would collapse into the nucleus entirely. Every atom in the universe would self-destruct almost instantly. Obviously, that doesn't happen. Atoms are stable. The ones in your body have existed for billions of years. Some of the hydrogen atoms in your body were created in the Big Bang itself, nearly 14 billion years ago, and they're still here, still intact, still doing their thing. So something is deeply wrong with the classical picture of orbiting electrons. Something fundamental has to be different about how electrons actually move. This is where quantum mechanics enters the story, and it enters not with a gentle knock, but with a complete demolition of everything physicists thought they knew about how small things behave. The first crack came from a Danish physicist named Niels Bohr. In 1913, just a couple of years after Rutherford's nuclear model of the atom, Bohr proposed something radical. He said, "What if electrons can only orbit at certain specific distances from the nucleus? Not any distance, not a smooth range of options, but only specific, quantized energy levels. An electron can be in the first level, or the second level, or the third level, but never in between. It's like a staircase versus a ramp. In the classical picture, an electron can be at any height. In Bohr's picture, it can only stand on specific steps. And Bohr added one crucial rule. An electron in the lowest energy level, the ground state, cannot radiate any more energy. It's already at the bottom step. There's nowhere lower to go. So it can't spiral into the nucleus. The atom is stable. Not because of some complicated mechanism, but because of a simple, seemingly arbitrary rule. There's a lowest step, and once you're on it, you stop. Now, Bohr's model was a brilliant hack. It explained a lot of things, including the specific colors of light that hydrogen emits, those precise spectral lines that had been puzzling physicists for decades. But it was still a somewhat classical picture. Electrons were still point-like particles, orbiting in neat circles, just restricted to certain orbits. And as physicists pushed deeper into the quantum world over the following decade, they realized that even this picture was too tidy. The reality is far weirder. The real breakthrough came in the mid-1920s, from a handful of physicists who essentially reinvented the rules of the universe. Werner Heisenberg, a young German physicist barely in his 20s, developed a mathematical framework called matrix mechanics. Erwin Schrödinger, an Austrian, independently developed a different mathematical framework called wave mechanics, built around his famous equation. And it turned out, after some initial confusion and rivalry, that these two frameworks were mathematically equivalent. They were two different languages, describing the same underlying reality. And what that reality looked like was nothing anyone had imagined. In quantum mechanics, an electron doesn't orbit the nucleus like a planet. It doesn't have a specific position at any given moment. Instead, what the equations give you is a probability distribution, a mathematical function that tells you the likelihood of finding the electron at any particular point in space if you were to look for it. The electron exists as a kind of cloud of probability surrounding the nucleus. Not a physical cloud, not a smear of charge, but a cloud of potentiality. The electron is more likely to be found in some places than others, but until you actually measure it, it doesn't have a definite position at all. This is one of those ideas that sounds like it must be a simplification, like surely the electron is really somewhere specific and we just don't know where. But no, quantum mechanics is very clear about this, and every experiment ever done confirms it. The electron genuinely does not have a definite position until it's measured. It's not that we're ignorant of where it is. It's that the question, where is the electron right now, doesn't have an answer. The universe itself hasn't decided yet. And here's why this matters for our question about empty space and solidity. Remember, the old picture was of a tiny electron orbiting in a vast empty space around the nucleus. But in quantum mechanics, that vast empty space isn't really empty. The electron cloud fills it, not with stuff exactly, but with probability, with the quantum mechanical presence of the electron. The electron's wave function, the mathematical object that describes its state, extends throughout the entire volume of the atom. It's denser in some places and thinner in others, but it's everywhere. So when we say the atom is 99.9% empty space, we're using the old language, the Rutherford language, the picture of a tiny nucleus and a tiny electron, with nothing in between. And that picture captures something real about the concentration of mass. Because yes, the mass of the atom is overwhelmingly in the nucleus, and the electron's mass is negligible in comparison. But in terms of the electron's quantum mechanical presence, the atom isn't empty at all. It's filled with the electron's wave function, a field of probability that defines the atom's size and shape and, crucially, its resistance to being pushed into by other atoms. Let's sit with that for a second, because it's a really important shift in how to think about atoms. The atom isn't a miniature solar system with mostly empty space. It's more like a fuzzy sphere of quantum probability centered on a dense nucleus. The fuzziness is the electron, and the reason you can't push one atom through another has everything to do with what happens when those fuzzy probability clouds overlap. This brings us to one of the most important principles in all of physics. It's called the Pauli exclusion principle, named after Wolfgang Pauli, an Austrian physicist who was as brilliant as he was abrasive. Pauli was famous for being devastatingly critical of other physicists' work. When he thought an idea was wrong, he'd say it wasn't even wrong, meaning it was so confused it couldn't even rise to the level of being testable and falsifiable. He was not a gentle man, but his physics was impeccable, and the principle he laid down in 1925 is one of the foundational rules of the universe. Here's what the Pauli exclusion principle says. No two electrons in the same system can occupy the same quantum state at the same time. Every electron has a set of quantum numbers that describe its state, including its energy level, its angular momentum, and a property called spin, which is either up or down. And no two electrons can have the exact same set of quantum numbers. They refuse. They absolutely will not do it. Now, this might sound like a minor bookkeeping rule, like a filing system for subatomic particles, but its consequences are staggering. The Pauli exclusion principle is why atoms have the structure they do. It's why the periodic table exists. It's why chemistry works. And it's a big part of why matter is solid. Here's the connection. When you push two atoms close together, their electron clouds start to overlap. And when that happens, the electrons from one atom start to share space with the electrons from the other atom. But the Pauli exclusion principle says no. You can't have two electrons in the same quantum state in the same place. So as the atoms get closer and the electron clouds are forced to overlap, some of the electrons have to jump to higher energy states to avoid violating the exclusion principle. And jumping to higher energy states costs energy, a lot of energy. This creates a resistance, a pressure, not pressure in the everyday sense, like air pushing against the walls of a balloon. This is quantum mechanical pressure, sometimes called degeneracy pressure, or exchange interaction. It's a force that arises purely from the quantum nature of electrons and the exclusion principle. The closer you try to push the atoms together, the more electrons have to be bumped up to higher energy states, and the more energy it costs, and the harder the atoms push back. And this quantum pressure is enormous. Not just big. Enormous. It's actually the dominant reason why solid matter resists compression. The electromagnetic repulsion between electron clouds plays a role, but the Pauli exclusion principle is the deeper, more fundamental reason why you can't squeeze matter into a smaller space. It's the reason why the floor holds you up. It's the reason why your bones don't crumble under the weight of your own body. It's the reason why a neutron star, a dead stellar core, with the mass of the sun compressed into a ball just 10 or 12 miles across, can resist the crushing force of its own gravity without collapsing into a black hole. Degeneracy pressure, the quantum mechanical consequence of the exclusion principle, is one of the most powerful forces in the universe, and it's happening right now, in every atom of your body. Here's the thing that makes this really beautiful. The Pauli exclusion principle isn't a force in the traditional sense. There's no particle carrying it. There's no field mediating it. It's a constraint on the wave function of fermions, which is the name for particles like electrons that have half-integer spin. It's a rule about what quantum states are allowed to exist. And yet, this abstract mathematical rule about the symmetry properties of wave functions produces a measurable, powerful, physical effect that holds up the entire material world. Think about what that means. The reason you don't fall through the floor, the reason your chair supports your weight, the reason buildings stand up and mountains don't collapse, isn't because there's some physical stuff in the way. It's because the quantum equations that describe electrons have a particular mathematical symmetry, an antisymmetry to be precise, that forbids certain configurations. The solidity of everything you've ever touched is, at bottom, a consequence of a mathematical rule about wave functions. That's one of those facts about the universe that, if you really let it sink in, changes how you think about what real means. Let's stay with this a while longer, because there's more to unpack about why the exclusion principle is so powerful, and it connects to some of the most dramatic objects in the universe. In an ordinary atom, the exclusion principle determines how the electrons arrange themselves around the nucleus. The first energy level, the lowest one, closest to the nucleus, can hold only 2 electrons, one spinning up and one spinning down. That's it. 2 electrons fill the first level, and the exclusion principle says no more can fit. So the third electron, in an atom with 3 or more electrons, has to go to the second energy level. And the second level can hold up to 8 electrons, because it has more available quantum states. And when that fills up, the next electrons go to the third level, and so on. This is why the periodic table has the structure it does. Hydrogen has 1 electron. Helium has 2, filling the first level completely, which is why helium is so stable and chemically inert. Lithium has 3, with the third electron forced up to the second level, which is why lithium is so reactive. That lone outer electron is eager to interact with other atoms. The entire architecture of chemistry, every reaction, every molecule, every protein in your body, ultimately traces back to the exclusion principle, determining how electrons stack up around nuclei, and it scales up to cosmic proportions. When a star like the sun exhausts its nuclear fuel, and can no longer sustain the fusion reactions that keep it inflated against gravity, it collapses. The outer layers puff off, and the core contracts until it's roughly the size of the Earth, but with the mass of the Sun. This is a white dwarf, an incredibly dense stellar remnant where the atoms have been crushed so close together that the electron clouds are fully overlapping. What holds the white dwarf up against the immense gravitational pressure? The Pauli exclusion principle, electron degeneracy pressure. The electrons physically cannot be pushed into the same quantum states, so they push back, and that quantum mechanical pushback is strong enough to resist the gravitational crush of a star. But even degeneracy pressure has its limits. In the 1930s, an Indian physicist named Subramanian Chandrasekhar, who was still in his early 20s at the time, calculated that if a white dwarf exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure can no longer hold it up. The electrons are forced to combine with protons, turning into neutrons, and the whole thing collapses further into a neutron star. And in a neutron star, it's neutron degeneracy pressure, the same Pauli exclusion principle, but now applied to neutrons instead of electrons, that holds the star up. A neutron star is essentially a giant atomic nucleus, 10 to 12 miles across, with a density so extreme that a teaspoon of its material would weigh about 6 billion tons. And if the neutron star is massive enough, even neutron degeneracy pressure fails, and the whole thing collapses into a black hole. There's nothing left to resist gravity. The exclusion principle has been overwhelmed, and matter falls inward without limit. So the same quantum rule that keeps your hand from passing through a table, the same principle that makes your chair feel solid, is also what holds up dead stars against gravitational collapse. And when that rule finally gives way under enough pressure, you get a black hole. The connection from your fingertips to the densest objects in the universe runs through the Pauli exclusion principle. But let's come back to Earth. Let's come back to you and the mattress you're lying on, and the question of why things feel solid. There's another layer to this that we haven't explored yet, and it has to do with what we mean by empty space inside an atom. Because remember, we said the atom is 99.9% empty. But what does empty actually mean here? In Rutherford's day, empty meant empty. Just vacuum, nothing there. The space between the nucleus and the electrons was as empty as the space between the stars. But quantum mechanics and, later, quantum field theory have completely changed that picture. In modern physics, there's no such thing as truly empty space. What we call empty space, even the vacuum, the space between atoms, the space between galaxies, is actually filled with quantum fields. Every type of fundamental particle has an associated quantum field that pervades all of space. There's an electron field, and a quark field, and a photon field, and a neutrino field, and a Higgs field, and so on. These fields are everywhere. They fill all of space, all the time. And what we call a particle, an electron, a photon, a quark, is really just a localized excitation of its corresponding field. A ripple, a vibration. Imagine a calm lake. The water is everywhere, smooth and still. Now imagine you drop a pebble in. Where the pebble lands, ripples spread out. Those ripples are localized disturbances in the water. In this analogy, the lake is the quantum field, and the ripples are particles. The electron isn't a tiny ball orbiting the nucleus. It's a stable excitation, a standing wave, in the electron field, which extends throughout all of space. And here's the thing about quantum fields. Even when there are no particles, even when there are no ripples, the fields are still there. And they're not perfectly still. Quantum mechanics tells us that these fields are always fluctuating, always jittering, because of the uncertainty principle. The Heisenberg uncertainty principle says you can't know both the exact value of a field and its exact rate of change at the same time. There's always some irreducible uncertainty, some quantum noise. And this means the vacuum, the supposedly empty space between atoms, is actually seething with activity. Tiny fluctuations in every quantum field, tiny blips of energy, popping in and out of existence on timescales so short they barely register. These fluctuations are sometimes described as virtual particles, pairs of particles and antiparticles that briefly flash into existence and then annihilate each other, borrowing energy from the vacuum for an instant before paying it back. Now, virtual particles is a somewhat misleading term. They're not really particles in the way we usually think of them. They're mathematical terms in the calculations of quantum field theory that correspond to these brief fluctuations. But they have real, measurable effects. One of the most famous is the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir predicted that if you place two uncharged metal plates extremely close together in a vacuum, they'll experience a tiny attractive force pushing them together, not from gravity, not from electrostatics, but from the quantum fluctuations of the electromagnetic field in the vacuum between and around the plates. The space between the plates is so narrow that it restricts which fluctuations can exist there, like how a guitar string can only vibrate at certain frequencies. Outside the plates, all fluctuations are allowed, so there's more quantum energy pushing on the plates from outside than from between them, and the plates get pushed together. This was experimentally confirmed in 1997 by Steve Lamoureux at the University of Washington, and it's been measured with increasing precision ever since. The empty space between those plates isn't empty. It's full of quantum field fluctuations, and those fluctuations exert a real, measurable force. That's extraordinary if you think about it. The nothing between two metal plates pushes them together. So when we go back to the atom and say it's 99% empty space, we need to be more careful about what we mean. The space inside the atom is empty in the sense that there's no solid matter there, no stuff in the way. But it's not empty in the quantum sense. It's filled with the electron's probability cloud, with quantum field fluctuations, with the invisible machinery of the forces that hold the atom together. It's full of physics, even if it's devoid of matter. And this brings us to another beautiful piece of the puzzle, the electromagnetic force, the one that makes electron clouds repel each other when atoms get close, isn't just some abstract push happening in a vacuum. It's mediated by photons, virtual photons, to be precise. When two charged particles interact, when two electrons repel each other, what's actually happening in the language of quantum electrodynamics, the quantum field theory of electromagnetism, is that they're exchanging virtual photons. One electron emits a photon, the other absorbs it, and the momentum transfer from that exchange creates the repulsive force. Quantum electrodynamics, or QED, was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, working independently. Feynman, in particular, developed a beautiful diagrammatic approach, Feynman diagrams, that lets you visualize these interactions. Two electrons come in, exchange a wiggly photon line between them, and bounce apart. It's a simple picture that encodes incredibly precise mathematics, and QED is, by some measures, the most precisely tested theory in the history of science. Its predictions match experiments to more than 10 decimal places. When you hear about the G factor of the electron, the anomalous magnetic moment, QED predicts it to a precision of roughly 1 part in 10 billion, and the measurement agrees. So the force you feel when you press your hand against a table isn't just electromagnetic repulsion in some vague sense. It's trillions of virtual photon exchanges happening every instant between the electron clouds of your skin and the electron clouds of the table surface. The invisible space between your hand and the table, that tiny gap we talked about, is teeming with virtual photons shuttling back and forth, carrying the force that keeps your atoms from interpenetrating. Now, let's go deeper. Let's ask what it would take to actually push atoms through each other, to really force matter to overlap. Under ordinary conditions, the electromagnetic repulsion and the Pauli exclusion principle make this essentially impossible. But nature does it. In extreme environments, under pressures and temperatures that make anything on Earth look like a gentle breeze, atoms can be crushed together until they lose their individual identities entirely. We already talked about white dwarfs and neutron stars. But let's spend a bit more time on neutron stars, because they're one of the most incredible objects in the universe, and they're directly relevant to our question about empty space and solidity. A neutron star forms when a massive star, much bigger than our Sun, runs out of fuel and its core collapses. The outer layers of the star blow off in a supernova, one of the most violent events in the cosmos, and the core that remains is crushed by gravity to unimaginable density. The electrons and protons in the core are forced together, merging into neutrons through a process called inverse beta decay. The proton and electron essentially combine, with the electron's negative charge canceling the proton's positive charge, producing a neutral neutron and emitting a neutrino that carries away some energy. What you end up with is a ball of neutrons, roughly 10 to 12 miles across, containing about 1.5 times the mass of the Sun. The density is almost inconceivable. A sugar cube of neutron star material would weigh about 1 billion tons. The surface gravity is about 200 billion times stronger than Earth's gravity. If you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a small nuclear bomb. And inside the neutron star, the empty space in atoms has been completely eliminated. There are no atoms anymore. No electron clouds, no gaps between nuclei. The matter has been compressed until the nuclei themselves are touching and merging, until the whole thing is essentially one giant nucleus. The empty space that makes up 99.9% of normal atoms has been squeezed out entirely. This is what it takes to actually fill in the emptiness of atoms. The gravitational force of a collapsing star, one of the most extreme events in the universe. That's the measure of how robust the forces are that keep atoms empty. It takes a supernova to overcome them, and even then, as we mentioned, the neutrons resist further compression through degeneracy pressure. The Pauli exclusion principle is still fighting, even at those insane densities. It takes yet more mass, pushing past about 2 to 3 solar masses, depending on the equation of state, which is still somewhat uncertain, before even neutron degeneracy pressure fails, and the whole thing collapses into a black hole. Now, you might be wondering about something. We've talked about the electromagnetic force keeping electron clouds apart, and the Pauli exclusion principle preventing electrons from occupying the same states. But there's another force at play inside the atom that we haven't spent much time on, and it's the reason the nucleus holds together at all. Because think about it. The nucleus is made of protons and neutrons. The protons are all positively charged, and like charges repel. So all those protons, crammed into a space 100,000 times smaller than the atom itself, should be violently repelling each other. The nucleus should fly apart. Why doesn't it? Because there's a force that's even stronger than electromagnetism. It's called, creatively enough, the strong nuclear force, or just the strong force. And it's the most powerful force in nature. At the scale of the nucleus, at distances less than about 1 femtometer, which is a millionth of a billionth of a millimeter, the strong force is about 100 times stronger than the electromagnetic force. It reaches across the tiny gaps between protons and neutrons and pulls them together with a grip so powerful that it overcomes the electromagnetic repulsion trying to blow the nucleus apart. The strong force is remarkable for several reasons. First, its incredibly short range. It only operates over distances comparable to the size of a nucleus. Beyond that, it drops off so sharply that it's effectively zero. This is why atoms don't just stick to each other through the strong force. It can't reach between atoms. It's confined to the interior of the nucleus. Second, the strong force doesn't actually act directly on protons and neutrons. Not fundamentally. It acts on the particles that make up protons and neutrons, which are quarks. This is another layer of the onion. Protons and neutrons aren't fundamental particles. They're made of 3 quarks each, bound together by the strong force, which, in its fundamental form, is called the color force, because quarks carry a property called color charge, which is analogous to electric charge, but comes in 3 types instead of 2. The force between quarks is mediated by particles called gluons, just as the electromagnetic force is mediated by photons. But gluons are very different from photons. Photons are electrically neutral. They don't carry the charge they transmit. But gluons carry color charge. They're both the messenger and the message. And this self-interaction gives the strong force its most bizarre property. It gets stronger as quarks move apart. With almost every other force in nature, the force weakens with distance. Gravity weakens. Electromagnetism weakens. But the strong force between quarks actually increases as you try to pull them apart. It's like a rubber band that gets stiffer the more you stretch it. This means you can never isolate a single quark. Pull 2 quarks apart, and the energy stored in the gluon field between them keeps increasing until there's enough energy to create a brand new pair of quarks out of the vacuum. Instead of separating the original quarks, you've just created more quarks. The original quarks snap back with their new partners, and you end up with 2 pairs of quarks instead of 2 individual quarks. This is called confinement, and it's one of the most remarkable features of the strong force. Quarks are permanently confined inside particles like protons and neutrons. They can never be free. Now, the strong force between quarks, mediated by gluons, is the fundamental force. But it leaks out a little bit, and the leftover, residual strong force is what binds protons and neutrons together in the nucleus. It's sometimes called the nuclear force, and it's the thing that keeps the nucleus from flying apart, despite all those positively charged protons repelling each other. And this residual strong force is what determines how much stuff can be packed into the nucleus, how dense the nucleus is, and therefore, how much of the atom's mass is concentrated in that tiny central point. The answer is almost all of it. More than 99.9% of the mass of an atom is in the nucleus, and the nucleus is 100,000 times smaller than the atom. The mass density of nuclear matter is roughly 230 trillion grams per cubic centimeter. 230 million metric tons per cubic centimeter. If you could fill a teaspoon with pure nuclear matter, it would weigh as much as a mountain, and yet the electrons, tiny, essentially massless by comparison, are what determine the size of the atom. The atom is as big as it is because of the electron cloud, which is governed by quantum mechanics and the electromagnetic force. So the size of an atom is set by quantum mechanics and electromagnetism, while the mass of an atom is set by the strong force and the quarks confined inside the nucleus. 2 different forces, 2 different scales, 2 different physics, coexisting inside the same structure, and the mismatch between them The fact that the mass-bearing part is so much smaller than the space-filling part is the reason atoms are 99% empty. Let's take a breath here and come back to the human scale, because I want to make sure all of this connects to something you can feel. Right now, you're lying somewhere comfortable. There's a surface beneath you, a mattress or a couch or a bed, and your body is pressing into it. The weight you feel, that familiar sensation of being held up, is gravity pulling your mass toward the center of the earth. Your mass, which is almost entirely in the nuclei of your atoms, those impossibly tiny, impossibly dense points. And what's holding you up, what's preventing you from sinking through the mattress and through the floor and through the bedrock all the way to the center of the earth, is the electromagnetic repulsion and the Pauli exclusion principle operating in the electron clouds of your atoms and the atoms of the surface beneath you. It's a strange mismatch when you think about it. The thing doing the pulling, gravity, is acting on your mass, which is in the nuclei, but the thing doing the pushing back, the resistance, the solidity, is coming from the electrons, which contribute almost none of your mass. The heaviest part of you is being supported by the lightest part of you. The nucleus has the mass. The electrons have the attitude. And it's the attitude, the quantum mechanical stubbornness of electrons refusing to share quantum states, that keeps everything from collapsing. And there's something poetic about Chandrasekhar's story too, by the way. He figured out this mass limit, the Chandrasekhar limit, while he was on a steamship from India to England in 1930. He was 19 years old. He'd just finished his undergraduate degree in Madras, and he was heading to Cambridge to study under Sir Arthur Eddington, who was at the time the most famous astrophysicist in the world. And on that long sea voyage, with nothing but time and a notebook, young Chandrasekhar worked out the mathematics of what happens when a star's core contracts under gravity. He showed that if the core is below about 1.4 solar masses, electron degeneracy pressure can hold it up. But above that limit, the electrons are forced to move so fast that special relativity becomes important. The relationship between speed and energy changes, and the degeneracy pressure can no longer keep up with gravity. The star collapses past the white dwarf stage. When Chandrasekhar presented this result to the Royal Astronomical Society in 1935, Eddington stood up and ridiculed it. Eddington couldn't accept the idea that a star could collapse beyond the white dwarf stage. He called it absurd. He argued, essentially, that nature wouldn't allow something so extreme. It was one of the most famous confrontations in the history of astrophysics, and Eddington was wrong, completely wrong. Chandrasekhar was vindicated decades later when neutron stars and eventually black holes were confirmed to exist. He eventually won the Nobel Prize in 1983, more than 50 years after that steamship calculation. But think about what that story means for our topic. A teenager on a boat, working through equations about the quantum pressure of electrons, predicted the existence of neutron stars and the possibility of black holes, decades before either was observed. The Pauli exclusion principle, this abstract rule about quantum states, when pushed to its mathematical limits, predicted the most extreme objects in the universe. The same force that keeps your hand from passing through a table, when scaled up to the mass of a star, shapes the destiny of suns. And there's one more thing I want you to appreciate about the relationship between the emptiness of atoms and the world you live in. It has to do with light. You might not think of light as being related to atomic emptiness, but it is, intimately. The reason materials have color, the reason the sky is blue and grass is green, and gold is golden, comes down to how photons interact with the electron clouds of atoms. When a photon, a particle of light, encounters an atom, it can be absorbed if its energy matches the difference between two energy levels in the atom's electron cloud. The electron jumps from a lower energy state to a higher one, absorbing the photon in the process. Later, the electron drops back down, emitting a new photon. The specific wavelengths of light that an atom absorbs and emits depend on its electron configuration, which depends on how many protons are in the nucleus, which determines what element it is. This is why every element has a unique spectral fingerprint, a set of specific wavelengths of light it absorbs and emits. Hydrogen emits red light at a very specific wavelength. Sodium emits bright yellow light, which is why sodium street lamps have that characteristic amber glow. Neon emits the reddish-orange light that gives neon signs their name. Each element has its own palette, determined by the quantum mechanical energy levels of its electron cloud. And this means that the colors you see in the world, every sunset, every rainbow, every leaf and flower and ocean, are ultimately a consequence of quantum mechanics operating in the empty space inside atoms. The electron cloud that makes atoms mostly empty space is the same electron cloud that absorbs and emits the photons that create color. The emptiness and the beauty are the same thing. When you see the blue of the sky, you're seeing sunlight that's been scattered by the electron clouds of nitrogen and oxygen molecules in the atmosphere. Blue light has a shorter wavelength and scatters more readily, so it reaches your eyes from every direction. But that scattering happens because photons interact with the quantum probability clouds of electrons orbiting nuclei in gas molecules 60 miles above your head. The beauty of a blue sky is a direct consequence of atomic emptiness. And when you see the glow of a fire, the warm orange and yellow light, you're seeing photons emitted by atoms in a state of extreme thermal agitation. The heat excites electrons to higher energy levels, and as they fall back down, they emit photons at specific wavelengths that your brain interprets as warm colors. Every campfire, every candle flame, every star in the night sky is a display of quantum mechanics in the electron clouds of atoms, playing out in the empty space around nuclei. Even the fact that some materials are transparent and others are opaque is about this same physics. Glass is transparent because the energy of visible light photons doesn't match any of the energy gaps in the electron configuration of silicon dioxide. The photons pass through without being absorbed. A brick wall is opaque because its atoms have electron configurations that absorb visible light efficiently. The difference between a window and a wall at the atomic level is a difference in electron energy levels, in the quantum mechanical structure of the empty space inside their atoms. So the emptiness of atoms doesn't just explain why things feel solid, it explains why things look the way they do. Color, transparency, reflection, refraction, all of these optical properties trace back to the quantum mechanical behavior of electrons in the nearly empty space around atomic nuclei. The emptiness is not just the absence of matter, it's the canvas on which the visible world is painted. There's a wonderful thought experiment that helps illustrate just how empty atoms really are, and how dramatic it would be if that emptiness were removed. Imagine you could somehow switch off the electromagnetic force and the Pauli exclusion principle, just for a moment, just to see what would happen. Without those two things holding atoms apart, without the electron clouds pushing against each other, matter would collapse. Not slowly, not gracefully, instantly. Every atom in your body would implode. The electrons would fall into the nuclei would merge, and all the matter that makes up you, all 7 octillion atoms, give or take, would compress into a single point of nuclear density. How big would that point be? Roughly the size of a very, very small grain of sand. Maybe smaller. You, as a nuclear density object, would be an impossibly tiny speck, so small You'd need a magnifying glass to find it, but so heavy that it would weigh exactly what you weigh now. Every ounce of you would still be there, just in a volume smaller than a dust mote. And if you did this for the entire Earth, removed all the empty space in every atom of the planet, the Earth would compress down to about the size of a marble, 9 millimeters across, roughly. But it would still have the same mass, about 6 trillion kilograms. A marble that weighs as much as a planet. You could hold it in your hand, if your hand still existed, but its gravitational pull would crush you. This thought experiment tells you something visceral about just how empty atoms are. The overwhelming majority of what you think of as you is empty space, held open by quantum mechanical forces. The stuff, the actual solid matter, is vanishingly small. And here's another angle on the same idea. Imagine you could enlarge an atom to the size of a large cathedral, Notre Dame, say, with its vast nave and soaring vaulted ceiling. In that atom cathedral, the nucleus would be a grain of sand sitting somewhere near the altar, a single grain, smaller than a poppy seed. And the electrons? They'd be like gnats, tiny buzzing specks whizzing around somewhere in the upper reaches of the nave, near the rose windows, far from the center. Everything between the gnat electrons and the sand grain nucleus would be empty. Just air, just space. You could walk from one side of the cathedral to the other and not encounter a single thing. And yet that cathedral atom holds its shape. It maintains its size. It interacts with neighboring atoms with precision and reliability. It forms bonds. It builds molecules. It creates the structures of life and matter with extraordinary consistency, all because of those forces we've been discussing: the electromagnetic repulsion, the quantum mechanical exclusion, the rules of the wave function. Let me tell you another story that helps bring all this together. It's about a man named Paul Dirac, and it involves one of the most beautiful predictions in the history of physics. Dirac was an English physicist, born in Bristol in 1902, and he was, by all accounts, one of the strangest people who ever lived. He was extraordinarily quiet, almost pathologically literal, and intensely private. He once sat through an entire lecture by another physicist and, when asked if he had any questions, said, "That was not a question. It was a statement." His colleagues joked that a unit of verbal output, called the Dirac, was 1 word per hour. But his physics was transcendent. In 1928, Dirac wrote down an equation that combined quantum mechanics with Einstein's special relativity to describe the behavior of electrons. This was necessary because the original Schrödinger equation, brilliant as it was, didn't account for the effects of special relativity, and electrons in atoms can move at significant fractions of the speed of light, especially in heavy atoms with lots of protons pulling them in. Dirac's equation was more than anyone bargained for. It didn't just describe the electron. It predicted the existence of something nobody had ever imagined: antimatter. The equation had 2 sets of solutions, one corresponding to electrons with negative charge and positive energy, which was expected, and another corresponding to particles with positive charge and negative energy, which was entirely unexpected. Dirac initially tried to explain away the second set, but eventually realized that the mathematics was telling him something real. There should exist a particle with the same mass as the electron, but opposite charge, an anti-electron, a positron. In 1932, an American physicist named Carl Anderson, working at Caltech, was studying cosmic rays using a cloud chamber, which is a device that makes the paths of charged particles visible as trails of condensation, like tiny contrails in a box. Anderson noticed tracks that curved the wrong way. They looked like electron tracks, but they curved in the opposite direction in a magnetic field, which meant they had the opposite charge. He had discovered the positron, exactly as Dirac's equation predicted. Now, why am I telling you about antimatter in a story about empty space and solidity? Because it connects to something fundamental about the nature of matter and the vacuum. When a particle meets its antiparticle, when an electron meets a positron, they annihilate each other. Both particles disappear, and their combined mass is converted entirely into energy in the form of photons. Pure E equals mc squared. The mass is gone, transformed into light. And the reverse can happen too. A sufficiently energetic photon can spontaneously convert into a particle-antiparticle pair, an electron and a positron materializing out of pure energy. This process of pair creation and annihilation is happening constantly in the quantum vacuum. Those virtual particle fluctuations we talked about earlier, many of them are exactly this: electron-positron pairs flashing into existence for the briefest moment and then annihilating back into nothing. The empty space inside an atom, between atoms, everywhere in the universe, is crackling with these events. They're too brief and too small to observe directly in most cases, but their cumulative effects are measurable. They contribute to the Lamb shift, a tiny change in the energy levels of hydrogen that was measured by Willis Lamb in 1947 and was one of the key observations that led to the development of quantum electrodynamics. So the emptiness of atoms is less empty than it appears. The space between the nucleus and the electrons isn't a true void. It's a quantum field in its lowest energy state, its ground state, but that ground state is not zero energy. It's a roiling sea of fluctuations, of virtual particles popping in and out, of fields that are always in motion, never truly still. The vacuum itself has energy, has structure, has properties. It's not nothing. It's the lowest something can be. This realization, that the vacuum is not truly empty, leads to one of the biggest unsolved problems in physics. When physicists try to calculate the total energy of all the quantum field fluctuations in the vacuum, the answer they get is absurdly large. In fact, if you use quantum field theory naively, without any cutoffs or adjustments, the vacuum energy density comes out to be infinite. That's obviously wrong, so physicists impose a cutoff at the Planck scale, the smallest meaningful scale in physics, and get a finite, but still ludicrously large answer. The predicted vacuum energy is roughly 120 orders of magnitude larger than what we observe cosmologically. That's not off by a factor of 10 or 100. It's off by a 1, followed by 120 zeros. This is sometimes called the worst prediction in the history of physics, and it's known as the cosmological constant problem, or the vacuum catastrophe. Nobody knows how to resolve it. Nobody has a satisfying explanation for why the observed vacuum energy is so spectacularly smaller than what quantum field theory predicts. And yet, the vacuum energy is not zero. We know that from the accelerating expansion of the universe, which was discovered in 1998 by two independent teams of astronomers studying distant supernovae. They found that the expansion of the universe isn't just continuing, it's speeding up. Something is pushing the universe apart, and the best explanation we have is that the vacuum itself has a tiny but non-zero energy density that acts as a kind of anti-gravity, a cosmological constant that drives the acceleration. So the empty space inside atoms, the space that makes them 99% void, is connected to one of the deepest mysteries in cosmology, the nature of the vacuum, the energy of nothing, the question of why space itself seems to have a small but real tendency to push things apart, and we don't fully understand any of it. Let's bring it back to something more tangible for a moment. Let's talk about what actually happens at the atomic level when you pick up an object. When you wrap your hand around a coffee mug, for instance. The atoms on the surface of your skin are approaching the atoms on the surface of the mug. Both sets of atoms have electron clouds, probability distributions of where their electrons are likely to be found. As the atoms get close, within a few angstroms of each other, an angstrom being 1/10,000,000th of a meter, roughly the diameter of a hydrogen atom, the electron clouds start to interact. First, there's the electromagnetic repulsion we discussed. The negatively charged electron clouds push against each other. But simultaneously, something more subtle is happening. The electron clouds are also attracting each other, weakly, through something called the van der Waals force. Here's how van der Waals forces work. At any given instant, the electron cloud of an atom isn't perfectly symmetrical. The electrons, being quantum mechanical, are fluctuating in their distribution, and at any moment, there might be slightly more negative charge on one side of the atom than the other. This creates a temporary, instantaneous dipole, a tiny imbalance of charge. And that tiny imbalance can induce a corresponding dipole in a neighboring atom, creating a momentary attraction between them. These attractions are individually tiny, but they add up, and they're responsible for a lot of the adhesion and cohesion in the everyday world. Van der Waals forces are why geckos can walk on walls and ceilings. The pads of a gecko's feet are covered in millions of tiny hair-like structures called setae, and each seta branches into hundreds of even tinier spatulae. These spatulae are so small that they make intimate contact with the surface at the molecular level, and the cumulative van der Waals forces across millions of these contact points are strong enough to support the gecko's weight. The gecko isn't using suction cups or glue. It's using quantum mechanical fluctuations in electron clouds to stick to the ceiling. That's astonishing. So when you pick up that coffee mug, the interaction between your atoms and the mug's atoms is a complex dance of electromagnetic forces. Repulsion keeps you from passing through the mug. Van der Waals forces and friction provide enough grip to hold it. Chemical bonds in the ceramic hold the mug together. And through all of this, no atom ever actually touches another. It's all forces, all the way down. Force fields interacting across tiny gaps of empty space that isn't really empty, and the information that creates the sensation of touch, the signal that travels up your arm and into your brain, telling you that you're holding something, is itself an electromagnetic phenomenon. The deformation of the electron clouds in your skin triggers nerve signals, which are electrochemical impulses traveling along neurons, which are long cells held together by electromagnetic forces, and chemical bonds, which are themselves electromagnetic. The force you feel and the sensation you experience are both electromagnetic, from beginning to end. Let's talk about chemical bonds for a moment, because they're another beautiful example of how quantum mechanics creates structure from emptiness. When two atoms form a chemical bond, what's happening is that their electron clouds are overlapping in a specific, controlled way. In a covalent bond, the simplest type, two atoms share a pair of electrons. The shared electrons form a region of higher probability between the two nuclei, creating a kind of electron bridge that pulls the nuclei toward each other. The two nuclei end up at a stable distance, not too close, not too far, where the attractive forces from the shared electrons balance the repulsive forces between the two positively charged nuclei. This bond is incredibly specific. The distance between the two nuclei in a given type of bond is precise to within a fraction of an angstrom. The angle between bonds is specific, determined by the geometry of the electron orbitals. This precision is why molecules have definite shapes, why water is bent at 104.5 degrees, why methane is a perfect tetrahedron, why DNA has its double helix. The geometry of the world, from the shape of a snowflake to the fold of a protein, comes from the quantum mechanical rules governing how electron clouds overlap and share. And all of this, all the structure and specificity of chemical bonds, happens in that empty space, inside and between atoms. The emptiness isn't a bug, it's a feature. The space between nuclei is where electrons roam, where probability clouds overlap, where bonds form, where chemistry happens. Without that emptiness, without that room for electrons to spread out and interact, there would be no chemistry, no molecules, no life. The emptiness of atoms is precisely what allows the rich, complex, structured world to exist. Think about that for a moment. If atoms were solid, dense little billiard balls with no internal structure, they'd bounce off each other, and that would be it. No bonding, no molecules, no water, no proteins, no DNA, no you. It's the quantum mechanical emptiness of atoms. The fact that electrons exist as probability clouds spread over relatively vast volumes of space, that allows the interactions and bonds and structures that make the material world possible. The emptiness isn't a deficiency, it's the canvas on which reality is painted. Let me tell you one more story, and this one goes all the way back to the very beginning. In the first few minutes after the Big Bang, the universe was unimaginably hot and dense. There were no atoms. There were no nuclei. There was a soup of quarks and gluons, so hot that the strong force couldn't bind them into protons and neutrons. This was the quark-gluon plasma, a state of matter that existed when the universe was less than a millionth of a second old. As the universe expanded and cooled, the quarks condensed into protons and neutrons. Within about 3 minutes, nuclear reactions fused some of those protons and neutrons into helium nuclei and tiny amounts of lithium. This is Big Bang nucleosynthesis, and it set the initial chemical composition of the universe, roughly 75% hydrogen, 25% helium, and trace amounts of lithium. Nothing heavier. No carbon, no oxygen, no iron, no silicon. All of those would be made later, inside stars. But here's the thing. For the first 380,000 years of the universe's existence, there were no atoms. Not because there weren't nuclei, there were plenty of those after the first few minutes, but because the universe was still too hot for electrons to be captured into stable orbits around them. The thermal energy was so high that every time an electron tried to settle into an orbit around a nucleus, a photon would come along and knock it loose again. The universe was a plasma, a sea of free nuclei and free electrons and photons, all mixed together in a hot, opaque fog. Then, about 380,000 years after the Big Bang, the universe cooled enough, to roughly 3,000 degrees Kelvin, that electrons could finally settle into stable orbits around nuclei. Hydrogen atoms formed. Helium atoms formed. For the first time, matter had the structure we recognize. Nuclei with electron clouds. Atoms with all that empty space inside them. And when that happened, something extraordinary occurred. The universe became transparent. Before atoms formed, photons couldn't travel far without bumping into a free electron and scattering. The universe was opaque, like fog. But once electrons were bound into atoms, the photons could travel freely. Light could move in straight lines through space for the first time. The fog cleared. We can still see that moment. The light released, when the universe first became transparent, is still traveling through space. It's been stretched by the expansion of the universe from visible light to microwave radiation, but it's still there. It's called the cosmic microwave background, and it was discovered in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs who initially thought the faint microwave signal they were detecting was noise from pigeon droppings on their antenna. They cleaned the antenna, shooed away the pigeons, and the signal remained. It was coming from everywhere in the sky, in every direction, uniform to one part in 100,000. It was the afterglow of the Big Bang itself, the oldest light in the universe, and it tells us what the cosmos looked like 380,000 years after its birth. That moment, when electrons settled into orbits around nuclei and atoms were born, was the moment the empty space inside atoms was created. Before that, there was no empty space in that sense, because there were no atoms. The universe was a dense, hot plasma where everything was touching everything. The atomic emptiness we've been exploring, the 99.9% void, came into being at a specific moment in cosmic history, and it immediately transformed the universe, making it transparent, allowing light to travel, eventually allowing gravity to pull matter together into stars and galaxies and planets, and, on at least one planet, into you. You are, in a very real sense, a structure made of emptiness, an arrangement of quantum fields and probability clouds organized around tiny, dense nuclei, held together by forces and rules that emerge from the deepest mathematics of the universe. The emptiness is not the absence of something. It's the presence of the conditions that allow complexity, chemistry, structure, and life. Now, there's something else I want to explore with you, because it pushes the strangeness of this whole picture even further. We've talked about why atoms feel solid, even though they're mostly empty. We've talked about electromagnetic repulsion and the Pauli exclusion principle and quantum field fluctuations. But there's a question underneath all of those. What actually is an electron? What is a proton? What are these things that create the forces and fill the probability clouds and make matter feel like matter? And the honest answer, the answer that modern physics gives us, is deeply unsettling. An electron is not a little ball. It's not a tiny speck of stuff. As far as any experiment has ever been able to determine, an electron has no internal structure, no size, no spatial extent. It's a point particle. 0 dimensions. When physicists probe the electron to determine how big it is, the answer keeps coming back. Smaller than we can measure. Current experiments set an upper limit on the size of the electron at roughly 1/10,000th of the size of a proton. It might have some tiny non-zero size, but if it does, it's incredibly, incredibly small. For all practical purposes, the electron is a mathematical point. And yet, this zero-dimensional point has mass, it has charge, it has spin, it has angular momentum. It interacts with every other charged particle in the universe through the electromagnetic field. It occupies quantum states. It forms probability clouds that define the size and shape of atoms. It's responsible for all of chemistry and, by extension, all of biology. An entity with no size creates a cloud that fills a volume 100,000 times larger than the nucleus. The emptiness of the atom isn't between two things. It is the thing. The electron's probability cloud is the atom's outer structure. Now, the proton and the neutron, the particles in the nucleus, are different. They're not point particles. They have internal structure. Each one is made of 3 quarks, held together by gluons. The proton has 2 up quarks and 1 down quark. The neutron has 1 up quark and 2 down quarks, and the quarks are bound so tightly by the strong force that they can never escape. But here's something really remarkable about protons and neutrons. Most of their mass doesn't come from the quarks inside them. The 3 quarks in a proton account for only about 1% of the proton's total mass. 1%. The other 99% comes from the energy of the gluon field, the energy of the strong force itself, binding the quarks together. It's pure E equals mc squared. The energy of the interaction is so large that it contributes almost all of the mass. Think about what that means for you. Your body has mass. You have weight. When you step on a scale, the number you see is almost entirely, about 99%, the energy of the strong force inside your protons and neutrons. You're not really made of stuff. You're made of energy. The quarks, the actual particles with rest mass inside your protons and neutrons, contribute almost nothing to your weight. It's the force between them, the energy of their interaction, that gives you substance. So here's the full picture, and it's wild. You're made of atoms. Atoms are mostly empty space. The tiny dense nuclei at their centers are made of protons and neutrons. Protons and neutrons are made of quarks, and quarks contribute only about 1% of the mass of the proton. The rest is energy, the energy of the gluon field. So your mass, your weight, the thing that gravity acts on to keep you pressed against the mattress right now, is overwhelmingly the energy of quantum fields, not matter in the solid, tangible sense. Energy, force, interaction, fields. And the solidity you feel, the resistance of the mattress, the firmness of the floor, that's the electromagnetic force and the Pauli exclusion principle, operating through electron probability clouds that are themselves excitations of a quantum field that pervades all of space. You are, in the most literal sense physics allows, a pattern of energy and information held together by the rules of quantum mechanics. The matter you think of as solid, tangible stuff is, underneath, a dance of quantum fields. Empty space that isn't really empty. Stuff that isn't really stuff. Forces that create the illusion of solidity from what is fundamentally a web of interactions. I want to take a detour here because there's a figure in the history of physics who thought deeply about exactly these questions, about the relationship between matter, fields, and reality, and his insights are worth spending time with. That person is Michael Faraday. Faraday was born in 1791 in the south of London, the son of a blacksmith who had recently moved the family from the north of England. He had almost no formal education. He went to work at age 13 as an apprentice bookbinder, and it was in the bookbinding shop that he started reading the books he was supposed to be binding. One of them was a popular science book by Jane Marcet that introduced him to chemistry and electricity, and it changed his life. Through a combination of persistence, brilliance, and almost comical good luck, Faraday managed to get himself a position as a laboratory assistant at the Royal Institution, working under the famous chemist Humphrey Davy. Over the following decades, Faraday became one of the greatest experimental scientists who ever lived. He discovered electromagnetic induction, the principle behind every electric generator and transformer in the world. He discovered the laws of electrolysis. He liquefied chlorine. He invented the Faraday cage. He discovered benzene. The list goes on and on, but the thing I want to focus on is his concept of fields. Before Faraday, most physicists thought of forces as acting at a distance. Two magnets attract or repel each other across empty space, and that's that. The force just reaches out and acts. Newton himself was uncomfortable with this idea, action at a distance. But he couldn't see an alternative. Faraday proposed something different. He said the space around a magnet isn't empty. It's filled with lines of force, a field, that extends outward from the magnet and influences anything that enters it. The force isn't transmitted instantaneously across a void. It's mediated by the field, which exists in the space between the objects. The field is real. It's a physical thing. It occupies space, stores energy, and transmits forces. This was a revolutionary idea. Faraday didn't have the mathematics to formalize it. He was self-taught and famously uncomfortable with equations. But James Clerk Maxwell later took Faraday's physical intuition and turned it into one of the most beautiful mathematical frameworks in physics, Maxwell's equations, which describe how electric and magnetic fields behave, how they create each other, and how they propagate through space as electromagnetic waves, which is to say, as light. And Faraday's insight that space is filled with fields, that forces are mediated by something real that exists in the space between objects, turns out to be one of the deepest truths in physics. In modern quantum field theory, everything is a field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of the quark field. Matter itself is just fields, vibrating in different ways. And the space between particles, the empty space inside atoms, is not a void. It's the ground state of these fields. Quiet, but not silent. Still, but not frozen. The lowest energy state, but not zero energy. Faraday, the blacksmith's son, with no formal education, intuited the fundamental nature of reality more than a century before quantum field theory made it rigorous. The space around a magnet, the space inside an atom, the space between galaxies, is not empty. It's full of fields, and those fields are what matter is made of. Let me circle back now to something practical, something you might be curious about. If atoms are 99% empty space, and the solidity we feel is all about forces and quantum rules, could we ever engineer a way to pass matter through other matter? Could we make something like a ghost, able to walk through walls? The short answer is, almost certainly not. At least not in any way that would preserve the structure of the matter passing through. Here's why. To push one atom through another, you'd need to overcome the electromagnetic repulsion and the degeneracy pressure from the Pauli exclusion principle. As we discussed, this takes extreme energy. You'd need pressures comparable to those inside a neutron star, and at those pressures, matter doesn't maintain its structure. Atoms aren't atoms anymore. Electron clouds are crushed, nuclei merge. The matter doesn't gently slide through, it's destroyed. But here's an interesting loophole. There are particles that can pass through matter almost effortlessly, and they do it all the time. They're called neutrinos. Neutrinos are among the most abundant particles in the universe. Every second, about 65 billion neutrinos from the sun pass through every square centimeter of your body. Right now, as you lie here, trillions of neutrinos are streaming through you every second, passing through your flesh and bones, and the mattress beneath you, and the entire Earth, as if none of it were there. They can do this because neutrinos don't interact through the electromagnetic force or the strong force. They only interact through the weak force, which is, as the name suggests, very weak, and through gravity, which at the particle level is inconceivably feeble. Since neutrinos aren't affected by the electromagnetic force, they don't care about electron clouds. The repulsion that keeps your hand from passing through a table simply doesn't apply to them, and since they don't feel the strong force, they don't interact with nuclei in the way other particles do. The atoms in your body are, to a neutrino, almost perfectly transparent. A neutrino could travel through a wall of lead a light-year thick, about 6 trillion miles, and have roughly a 50% chance of passing through without interacting with a single atom. That's how ghostly they are. They're the closest thing in nature to something that can pass through solid matter. So the answer to, why can't things pass through other things, is partly, some things can. Neutrinos do it effortlessly. Photons do it through transparent materials. Even some atoms and molecules can tunnel through barriers, thanks to a quantum mechanical process called quantum tunneling, where a particle can appear on the other side of a barrier that it doesn't have enough energy to climb over classically. This actually happens in nature. Radioactive alpha decay, where a helium nucleus escapes from a larger nucleus, happens by quantum tunneling. The alpha particle doesn't have enough energy to overcome the strong force binding it to the nucleus, but quantum mechanics gives it a small probability of being found on the other side of the barrier anyway. And over long enough timescales, that small probability adds up. Quantum tunneling happens in the sun too. The nuclear fusion reactions that power the sun, that convert hydrogen into helium and release the energy that lights up the solar system, depend on quantum tunneling. The protons in the sun's core are moving fast because of the extreme temperature, about 15 million degrees. But even at those temperatures, they don't have enough kinetic energy to overcome the electromagnetic repulsion between their positive charges and smash into each other. Classically, fusion shouldn't happen in the sun. The temperature is too low, but quantum tunneling gives the protons a tiny probability of appearing close enough together for the strong force to grab them. And given the enormous number of protons in the sun's core, that tiny probability is enough to sustain fusion reactions that produce the energy output of 400 trillion watts every second. Without quantum tunneling, the sun wouldn't shine. Without quantum tunneling, stars couldn't fuse elements, planets wouldn't form, and life wouldn't exist. The same quantum mechanics that makes atoms mostly empty and matter weirdly insubstantial is also the reason stars work and the universe is lit up. It's all connected. Now, quantum tunneling on the macroscopic scale, a person tunneling through a wall, is theoretically possible, but practically impossible. The probability is so vanishingly small that if you stood against a wall and waited, the expected time before you'd tunnel through is longer than the age of the universe, by a factor that I can't even express in normal numbers. We're talking about a probability with so many zeros after the decimal point that there aren't enough atoms in the observable universe to count them. So while the laws of physics don't strictly forbid you from walking through a wall, the odds are so ludicrously small that it will never, ever happen. But the fact that it's not zero, the fact that quantum mechanics puts a non-zero probability on it, is itself a remarkable statement about the nature of matter and space. The boundaries between objects, the surfaces that feel so solid and definite, are, at the quantum level, slightly fuzzy. Not perfectly sharp edges where matter ends and nothing begins, but smooth probability distributions that tail off gradually, asymptotically approaching zero but never quite reaching it. Your atoms don't have hard edges. They have soft, probabilistic boundaries that technically extend to infinity, getting weaker and weaker, but never truly disappearing. Your electron cloud, technically, extends to the edge of the observable universe. It's just that the probability of finding your electron out past your skin is so small that it's meaningless. But mathematically, it's there. You are, in a quantum mechanical sense, slightly everywhere. Your boundary is not a wall. It's a gradient. Let's talk about one more force, the one we haven't spent much time on, gravity. Because gravity has a peculiar relationship with the emptiness of atoms that's worth exploring. Gravity, as Einstein showed in his general theory of relativity, isn't really a force at all. It's the curvature of space-time, caused by the presence of mass and energy. Massive objects bend the fabric of space-time around them, and other objects moving through that curved space-time follow paths that we interpret as gravitational attraction. The Earth doesn't pull you down. The Earth's mass curves the space-time around it, and you follow a curved path through that space-time that happens to lead toward the center of the Earth. The mattress interrupts your path, and the electromagnetic forces and Pauli exclusion in the mattress atoms push back against you, and that push is what you feel as weight. Now, gravity is by far the weakest of the four fundamental forces. The electromagnetic force between two protons is roughly 10 to the 36th power times stronger than the gravitational force between them. That's a 1, with 36 zeros after it. Gravity is almost inconceivably weak compared to electromagnetism. The fact that gravity dominates the large-scale universe, pulling stars together, shaping galaxies, holding planets in orbit, is only because gravity is always attractive. It never cancels out, while electromagnetic forces can be positive or negative and tend to cancel in large, electrically neutral objects. But gravity has something the other forces don't. It's universal. It acts on everything that has mass or energy. And as we've discussed, the empty space inside atoms isn't really empty. It has quantum field fluctuations. It has vacuum energy. And that vacuum energy, whatever its true value is, gravitates. It has a gravitational effect. This is the connection between the emptiness of atoms and the expansion of the universe. The vacuum energy in empty space, if it's positive, acts as a kind of cosmological constant, a repulsive gravitational effect that pushes the universe apart. And the measurements suggest it is positive, and it is pushing the universe apart, faster and faster as the universe expands, and there's more empty space for the vacuum energy to fill. So the emptiness of atoms, the empty space that makes up the vast majority of every atom in your body, is gravitationally active. It contributes to the energy content of the universe. It participates in the expansion of space itself. The nothing between your nuclei and your electrons isn't nothing, it's something, and that something is pushing the universe apart. This is where we start touching the really deep mysteries, the ones that nobody has answers to yet. Why does the vacuum have the energy it does? Why is the cosmological constant so small compared to what quantum field theory predicts, but not zero? What is the dark energy that makes up roughly 68% of the total energy content of the universe? And is it really just vacuum energy, or is it something else entirely? And then there's the question of quantum gravity. We have a magnificent theory of gravity, Einstein's general relativity, which describes space-time as a smooth, continuous fabric that curves in response to mass and energy. And we have a magnificent theory of quantum mechanics, which describes matter and forces as quantized, probabilistic, fundamentally discrete at the smallest scales. But these two theories are fundamentally incompatible. They can't both be right, at least not in their current forms, because they make contradictory predictions when you push them to extreme conditions. The place where the conflict becomes most acute is inside a black hole, at the singularity, where general relativity predicts that matter is crushed to infinite density in zero volume, and quantum mechanics says that's not possible. You can't confine something to zero volume without violating the uncertainty principle. And the conflict also matters at the very beginning of the universe, in the first fraction of a second after the Big Bang, when the universe was so small and so dense that quantum gravitational effects should have been important. Finding a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics, is the biggest unsolved problem in fundamental physics. String theory is one approach, which proposes that the fundamental entities aren't point particles but tiny, vibrating strings of energy, and the different particles we observe are different modes of vibration. Loop quantum gravity is another approach, which proposes that space-time itself is quantized, made of tiny, discrete loops at the Planck scale. There are other approaches too. None of them is complete. None of them has been experimentally tested. And until one of them is, we have this fundamental crack in our understanding of reality, a crack that runs right through the center of our question about atoms and emptiness. Because here's the thing, when we say an atom is mostly empty space, we're talking about space, space-time. the fabric that general relativity describes. And we know that space-time is smooth and continuous at ordinary scales. But we suspect, though we can't prove, that at the Planck scale, roughly 10 to the minus 35 meters, about 20 orders of magnitude smaller than a proton, space-time itself might be quantized. It might have a granular structure. It might be made of something. At the very smallest scales, the emptiness inside an atom might not be continuous empty space, but some kind of quantum foam, a seething, roiling structure of geometry and topology, constantly fluctuating. If that's true, and we genuinely don't know, then the emptiness inside atoms isn't empty even in the spatial sense. The space itself might have structure, might have information, might be a dynamical entity with its own properties and behavior. The nothing between the nucleus and the electrons might be the most complex thing in the universe, a quantum gravitational structure that we don't have the physics to describe yet. Let me tell you about one more remarkable idea that ties together many of the threads we've been pulling on tonight, and it's about the relationship between information and physics. In the 1970s, the physicist Jacob Bekenstein and, independently, Stephen Hawking made a startling discovery about black holes. They found that a black hole has entropy, a measure of disorder or information content, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This is the holographic principle in its earliest form, and it suggests something extraordinary about the nature of space and information. In ordinary physics, if you have a room full of stuff, the amount of information needed to describe everything in that room scales with the volume. More space, more stuff, more information. But for black holes, the information content scales with the surface area, not the volume. It's as if all the information about what's inside the black hole is somehow encoded on its surface, like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. This idea has been extended, and some physicists now suggest that the holographic principle might apply to the entire universe, that the three-dimensional space we live in, including all the empty space inside atoms, might be a kind of projection from information encoded on a distant two-dimensional surface. The emptiness inside an atom might not be a three-dimensional void at all. It might be an emergent property of information processing happening in a fundamentally different, lower-dimensional reality. Now, this is very much at the speculative frontier of physics. It's not established science. It's a leading idea in theoretical physics, supported by mathematical arguments and some indirect evidence. But it hasn't been experimentally confirmed. But it gives you a sense of how deep the question, what is the empty space inside an atom, goes. The answer might not just be about forces and fields and quantum mechanics. It might be about the fundamental nature of space itself, about information, about what it means for a three-dimensional world to exist. And I want to circle back to something Faraday would have appreciated about all of this. Faraday believed that fields were the fundamental reality, and that matter was secondary. He would not have been surprised to learn that atoms are mostly empty space, because in his view, atoms were never really solid things. They were concentrations of field strength, knots in the fabric of force that fills all of space. The empty space inside an atom isn't a void in which the atom sits. The atom is the field, and the space is the atom, and the distinction between matter and empty space is, at bottom, a distinction between regions of higher and lower field strength, not between something and nothing. Modern quantum field theory says essentially the same thing, just with more mathematical precision. Everything is fields. Particles are excitations. Space is the ground state. The emptiness of atoms is the resting state of the quantum fields, and the matter of atoms is the excited state. They're the same thing at different energy levels. The distance between empty and full is a matter of degree, not of kind. Let's bring this journey back to where we started, to where you are right now. You're lying in the dark, or maybe in dim light, and your body is resting on something. You can feel the surface beneath you. You can feel the weight of the blanket on top of you. You can feel the gentle pressure of your own body settling into the bed. Every one of those sensations, every point of contact, every ounce of pressure, is the electromagnetic force and the Pauli exclusion principle at work. Your atom's electron clouds are interacting with the electron clouds of the mattress and the blanket and the pillow, exchanging virtual photons, following the quantum rules that govern their probability distributions, producing the macroscopic sensation of solidity and support. And none of it is atoms touching atoms. There's always a gap, always a tiny space, a fraction of an angstrom, where the electron clouds can't quite overlap because the exclusion principle won't let them, and the electromagnetic repulsion pushes them apart. What you feel as solid contact is a quantum force field interaction, a conversation between electron clouds. Meanwhile, inside every atom of your body, there's that vast emptiness, that cathedral-sized space around a grain of sand-sized nucleus. And it's filled not with nothing, but with the electron's probability cloud, with the fluctuations of quantum fields, with the residual presence of the electromagnetic and strong and weak and gravitational interactions that make the atom what it is. The empty space inside you is alive with physics. It's not a void. It's the most densely structured nothing you can imagine. And the nuclei at the centers of your atoms, those impossibly tiny, impossibly dense points that hold 99% of your mass, they're made of quarks and gluons, bound by the strong force, and the mass you feel as your own weight is overwhelmingly the energy of that binding, the energy of the interaction, not the mass of the quarks themselves. You are made, quite literally, of energy organized by quantum rules into patterns that persist for decades, that think and feel and wonder about the nature of atoms. The neutrinos are passing through you right now, trillions of them every second, straight through every atom, as if you weren't there. To a neutrino, you are transparent. You are empty space. The solidity you feel, the heaviness, the substance, the reality of your body, is invisible to them. They pass through you, the way you pass through a beam of light, without noticing. And the cosmic microwave background, the oldest light in the universe, is passing through the walls of your room right now. It's everywhere, in every direction, a faint microwave glow left over from the moment, 380,000 years after the Big Bang, when atoms first formed, and the universe became transparent. That light has been traveling for nearly 14 billion years, through the expanding emptiness of intergalactic space, through the emptiness inside every atom it's encountered along the way, and some of it is passing through you right now. You're bathed in the afterglow of creation. It's a lot to hold in your mind, and you don't have to hold all of it. That's the beauty of a topic like this. You can let the details blur and just keep the feeling, the sense of how strange and beautiful and deeply non-obvious the world is at its most fundamental level. The table feels solid because of quantum mechanics. The floor holds you up because electrons refuse to share quantum states. The mass of your body is mostly the energy of the strong force. The space inside your atoms is filled with quantum fields that are never truly still, and the emptiness between you and everything you touch is alive with virtual photons carrying the electromagnetic force at the speed of light. Nothing is truly solid. Nothing is truly empty. Everything is in between, a spectrum of field strengths and quantum probabilities and force interactions that produce, from the interplay of abstract mathematical rules, the warm, tangible, sensory world you experience every day. And that might be the most wonderful thing of all, that the universe doesn't need solid building blocks to build a solid world. It doesn't need stuff to make stuff. It just needs fields and rules, and from those emerges everything. The hardness of diamond, the flow of water, the warmth of skin, the weight of a sleeping body settling into a mattress. All of it, from fields and emptiness, and the quantum rules that weave them together. So here's the answer to the question we started with. Why are atoms 99% empty space, but nothing passes through anything? Because the emptiness isn't a gap in the defenses, it's the defense, the vast probability cloud of the electron, filling all that space around the nucleus, I as the atom's boundary. And that probability cloud isn't passive, it's governed by quantum rules, the Pauli exclusion principle, the electromagnetic interaction, the topology of the wave function, that make it extraordinarily effective at repelling other atoms. The emptiness is not a weakness, it's the mechanism. It's how atoms say no, and they say it with absolute authority. The forces involved are immense. The quantum mechanical pressure that resists compression is powerful enough to hold up dead stars. The electromagnetic repulsion between electron clouds operates with a speed and precision that no macroscopic barrier can match. The empty space inside your atoms is, paradoxically, the most strongly defended space in the universe. You can't push your hand through a table because the emptiness in your atoms and the emptiness in the table's atoms are both quantum mechanically armed. They're bristling with forces. They're defended by the deepest rules of the universe. The nothing between your nuclei and your electrons is not a passive void. It's an active, energetic, quantum mechanically enforced exclusion zone. It's the strongest no in nature. And yet, it's gentle enough to let neutrinos pass through without noticing. It's precise enough to allow chemical bonds to form, molecules to assemble, proteins to fold, DNA to replicate. It's flexible enough to permit quantum tunneling, to let stars fuse hydrogen into helium, to let radioactive nuclei decay. The same forces that make matter feel solid also allow the incredible, subtle, beautiful interactions that make the complex universe possible. Lying here in the dark, you're a marvel of quantum architecture, 99% empty space, held together by forces and rules that are invisible, immaterial, and unbreakably strong. Everything you feel, every sensation of weight and warmth and contact, is a quantum field interaction happening at scales too small to see, too fast to perceive, too abstract to touch. And yet you feel it. It's as real as anything can be. The atoms in your body have been around for billions of years. The hydrogen was made in the Big Bang. The carbon and oxygen and nitrogen were forged inside stars that lived and died before the sun was born. The iron in your blood was created in a supernova explosion, a dying star's final act, scattered into space, and eventually gathered by gravity into the rocky planet you call home. And all of those atoms, through all those billions of years, have been mostly empty. Vast internal spaces, tiny dense nuclei, electron clouds governed by quantum mechanics. They've been empty since the moment they formed, 380,000 years after the Big Bang, when the universe cooled enough for electrons to settle into orbits. And all that time, through all that emptiness, they've been solid. They've held their shape. They've formed molecules and minerals and oceans and atmospheres and, eventually, a living body lying in the dark, wondering about atoms. The emptiness was never the problem. The emptiness was the point. Without it, without that vast quantum mechanical space for electrons to spread into, for probability clouds to form, for chemical bonds to happen, none of this would be possible. Not stars, not planets, not water, not air, not you. The solidity of the world isn't despite the emptiness of atoms, it's because of it. And that's a beautiful thought to fall asleep to. That the nothing inside you is not nothing. That the emptiness is full of purpose. That the space between your particles is where the magic happens. That you are, in the deepest sense physics allows, made of almost nothing, held together by almost everything. The forces are still at work. The electron clouds are still humming. The virtual photons are still shuttling back and forth between every atom you're touching and every atom that's touching you. The strong force is holding your nuclei together with the power of a star. The quantum fields are fluctuating in the vacuum inside every atom of your body, and gravity, gentle, patient gravity, is pulling you softly into the surface beneath you, curving the space-time around your mass, and you're pushing back with the stubborn quantum refusal of your electron clouds. And that push and pull is the feeling of being here, of being real, of being a body in a bed, in a world that feels solid, even though it's almost entirely empty. 99% nothing, 100% real. And the distance between those two truths is where all of physics lives. Let that settle in. Let it sit softly in your mind, like the weight of a blanket. You don't need to hold on to all of it. The atoms will keep doing what they do. The forces will keep the world solid. The quantum fields will keep humming in the dark. And you can rest now. Rest on a surface that isn't really touching you, in a body that's mostly empty space, in a universe that's made of fields and energy and beautiful, unbreakable rules. Everything is held. Everything is supported. Everything is exactly as solid as it needs to be. The emptiness is not an absence. It's a presence. It's the presence of the quantum world, doing what it does, quietly, precisely, faithfully, in every atom, in every moment, everywhere, always. And it's doing it right now, right here, in you. Rest.